Hello, my name is Itzhak and I'm a PhD candidate in the Technion, Israel Institute of Technology, supervised by Professor Cohen and Professor Jacob Benesty. Today, I would like to present our work on robust differential beamforming with rectangular arrays. Let's start with a short introduction. In this work, we address speech signals, which are typically only observable in the presence of background noise, which might heavily degrade their quality. To cope with the background noise, which could consist, for example, of white noise and directional interferences, such as other human speakers, it's very common to employ a sensor array or a microphone array. The corrupted speech, as we can see right here in the illustration, is simultaneously sampled by the sensor array. Then the samples are filtered or multiplied by a spatial filter, which is usually referred to as beamformer. The output of the beamformer is an estimate of the clean speech. Over the years, numerous beamformers have been proposed, but differential beamformers are considered particularly appealing, as they exhibit a small array size, a frequency-invariant beam pattern, and they are also potentially capable of achieving high array directivity. Uniform linear arrays, or ULAs, are probably the most common type of differential beamformers, as they are the simplest to design, apply, and analyze. They are constructed from evenly spaced microphones, which are very often omnidirectional. Uniform rectangular arrays, or UArrays, may be seen as generalization of ULAs constructed by stacking ULAs in parallel. They tend to exhibit a preferable beam steering performance with respect to ULAs. In this work, we focus on UArrays. So what's the problem? Well, it's well known that high directivity differential beamformers suffer from sensitivity to white noise. This problem is particularly severe in low frequencies and may result in a significant degradation in the quality as well as in the intelligibility of the enhanced speech. So it implies that we may be able to further enhance the speech signals by mitigating this sensitivity to white noise. So what's our solution? In this work, we present a two-dimensional multi-stage spatial mean operator. The operator is applied to the noisy speech observations prior to the application of the differential beamformer. The spatial mean operator exhibits two design parameters which enable high design flexibility. These parameters are in charge of setting the number of mean stages in the array columns and row respectively. As a consequence, they provide a mean to control the trade-off between the robustness to white noise and the array directivity. To motivate, we demonstrate the robust differential approach on speech signals in a reverberant environment. We consider an 8 meters on 8 meters on 3 meters reverberant room with the parameter T60 equals 150 milliseconds. The Z equals 1.5 meter plane of the reverberant room is shown right here in the illustration. And we can see that in the middle of the room, around the point 4, 1.5, we have a URA with mx equals my equals 5 microphones. We have here a desired speech signal source, which is in the end fire with respect to the x-axis and in the broadside with respect to the y-axis. And additionally, we have two equally powerful directional interferences, which are marked in red, and as well as uncorrelated white noise, which naturally exists in the microphones and is 10 dB weaker than each of the direction interferences, so that the input signal to noise ratio with respect to the reference microphone right here is exactly 0 dB. And we employ the maximum directivity factor beamformer with 3 configurations of the two design parameters, which are denoted respectively by QC and QR. Okay, so now let's listen to the enhanced signals with the maximum directivity factor beamformer. First of all, let's hear what happened when QC and QR both equal 0, meaning when the spatial mean operator doesn't work at all.
Draw every outer line first, then fill in the interior.
And we can hear that the white noise is considerable. Now let's hear what happens when QC and QR both equal 1.
Draw every outer line first, then fill in the interior.
So we could sense some kind of an improvement. And let's see what happens when QC and QR are equal to.
Draw every outer line first, then fill in the interior.
And we could clearly sense that in this case, the white noise is greater attenuated than in the previous two cases. Okay, now let's examine the PESC and STOI scores of the demo we've just listened to. We also show here in the bottommost rows the appropriate scores with the null-constrained maximum directivity factor beamformer. So first of all, we observe that considering this case and these configurations, the higher the configurations, the better the performance in terms of both scores. And it's mostly stressed right here in the PESC scores, in which we can see that with both beamformers, changing the configuration from QCQRs both equal 0 to the case in which both equal 2 yields an improvement of approximately 0.3. So let's demonstrate how the two-dimensional spatial mean operator works. Let's assume, for example, that a desired speech signal is impinging on the array from the azimuth angle theta, and the speech signal is corrupted by a noise field, which, as we said before, may consist of white noise and directional interferences. And we have here also a U array, which consists of mx microphones along the x-axis with an inter-element spacing delta x, and my microphones along the y-axis with an inter-element spacing delta y. Now we present two design parameters, QC and QR, which, as we mentioned before, control the number of mean stages along the columns and rows of the array, respectively. Now, with QC and QR equals 0, 0, the spatial mean operator doesn't operate at all. Now let's assume that we want to set QC/QR to equal 1, 0. Then the first row of the array with the new configuration is generated by summing together the first two rows of the array with the current configuration, as we can see right here. And the second row of the array with the new configuration is generated by summing the second and third row of the array with the current configuration. And we repeat this process mx minus 1 times, which is in our case 4 times. And this yields a 4 by 5 microphone array with the configuration of 1, 0. Now let's assume that you would like to construct the configuration QCQR equal 1, 1. So we do exactly the same thing. However, this time we operate along the rows and across the columns. So we sum the first and second column with the existing configuration to generate the first column with the new configuration, the second and the third column of the current configuration to generate the second column of the new configuration, up to a total of my minus 1 times, which is once again 4. So obviously this process may repeat itself again and again, up to mx minus 1 times along the columns and my minus 1 times along the rows. And we end up with what can be regarded as a matrix of observation means. So now let's see the entire beamforming flow with the robust differential beamforming. So as a first step, we apply the multistage spatial mean operator to the noisy speech samples, as we can see right here, and obtain a matrix of observation means. Then we stack this matrix into a vector by its columns to obtain a vector of observation means. Then we apply a high-directivity differential beamformer to this vector to generate an estimate of the clean speech. So let's now examine with the following simulation parameters and see what happens to the white noise gain and directivity factor when the frequency equals 3 kHz. Now, these measures quantify the level of white noise rejection and spherically isotropic diffuse noise rejection merely resulted by the application of the spatial mean operator. Therefore, they're independent of the differential beamformer which comes next. However, they are a function of the rectangular array structure and the desired signal incident angle theta. So for example, in this case, when theta equals 0, it's intuitively clear that averaging along the rows would be more beneficial than averaging along the columns, since the desired signal is in fact in the broadside with respect to each ULA along the y-axis. So this practically means that applying the mean operator along the rows actually resembles the application of a series of delay and sum beamformers, which are known to be optimal in terms of the white noise gain. And we also see that the values on the upper triangular right here are preferable in terms of the directivity factor. And so considering that and keeping in mind that we wouldn't like QC and QR to be too large, in order to leave enough degrees of freedom for the beamformer, we may consider these configuration here, which are marked in gray, to be optimal. Okay, so next we investigate the white noise gain here in the upper row and the directivity factor in the bottom row with two beamformers, two high directivity beamformers. First one on the left is the maximum directivity factor beamformer, and we also have on the right its null constraint version, which is designed with two distinct nulls in theta 1 equals 90 degree and theta 2 equals minus 70 degree. So first of all, we can see that with both beamformers, as the values of QC, QR grow, the white noise gain improves, and this is with great accordance to what we've just seen. And it's particularly interesting to focus on the 1 kilohertz frequency, since the human ear sensitivity to this frequency is very high. However, many high directivity differential beamformers tend to exhibit white noise amplification in it, as we can see right here. So we can see that by simply choosing QC and QR to equal 2, as we can see in this curve, over the case in which they are 0, which is the basic case in which the special mean operator doesn't work at all, we can see that there is a 10 dB difference between the two configurations with the maximum directivity beamformer, and with its null constraint version, there is a 5 dB improvement. Okay, so on the contrary, we do note that as the white noise gain improves, the directivity factor in both cases deteriorates. However, this is probably negligible in most cases, as the degradation in performance is around 1 or 2 dBs. So let's sum everything up. In this work, we have introduced a robust approach for rectangular differential beamforming. The key idea was to employ a two-dimensional spatial mean operator onto the noisy speech observations prior to applying a high directivity beamformer. The spatial mean operator is controlled by two design parameters, which enable a high design flexibility in controlling the white noise robustness versus array directivity trade-off. We have also demonstrated on speech signals in reverberant environment that the robust approach enables further improvement of the enhanced signals in terms of both their quality and intelligibility. And thank you all for listening.